Hey guys, in this last section of the course, 12.2, Transforming to Achieve Linearity, we're going to look at, again, quantitative relationships, scatter plots, and see, if not linear, what can we do? Next year, you'll learn different strategies like quadratic regression or power regression, logistic regression. But what we're going to do in this last section here is try and identify the relationship, and if we can, if it is parabolic in nature, can we undo that to make the data linear and use the technique we're familiar with, linear regression. So use transformations of powers and roots to achieve linearity. Make predictions from the least squares regression line. We're really good at that. We just have to remember that if the data is transformed, what's the prediction we're actually making? And using transformations involving logarithms to achieve linearity for a relationship between two variables, determining which transformation is better, power or logs, or whatever it happens to be. You'll recall that in Chapter 3 we analyzed quantitative variables in a linear pattern, and if they were curved, we had a problem. So this is trying to solve that issue. Once the data has been transformed, we can use our strategy of a least squares regression line to generate a useful model, and assuming the conditions are met, make an estimation and test a claim and do all those things that we like to do. So this idea of taking data and applying such a function like a logarithm, square root, power, whatever it happens to be, that's called transforming the data. And we'll take a look at how that works. Basically, we're trying to make nonlinear and straighten them out. So our first example here is looking at the length and weight of fish. So you've got your data here, length and weight. And here, without transforming any of the data, if you were to graph this data here in a scatter plot, you have this curved relationship. If you tried to fit a line to that, hopefully you'd recognize that some of the points are going to fall above, some below, but it's going to follow some kind of pattern. This residual plot would not look good. Very clearly curved or parabolic. So the question is, what do we do? Well, the relationship that exists between length and weight is, and we'll just go through this example first, you don't need to know this, but while length is measured really in one dimension, weight is a three-dimensional measurement. And so what we could do is one of two things. We could take all the weights and cube root them to undo that that three-dimensional idea of weight and turn it into one dimension. Or, similarly, we could cube the one-dimensional length and graph it against weight. Choosing either of those results in a linear relationship, kind of putting them on the same level power-wise. Now, either one is fair to do. You can see that the data is kind of truncated down here, tends to spread out. The opposite is true if you cube root the weight, where the data tends to be truncated out there and more spread out that way. Either one is fine, and ultimately what we'll do is really not worry about that in this class. We'll come up with a strategy that will work in every case, not just, oh, do I need to square root it, cube root it, what do I do with this relationship? Because just looking at this, I'm not sure even I would have been like, oh, clearly that's a cube root relationship as opposed to square root or even, fourth root or fourth power. Now, in this example, if we take a look at the transformed data that was then, a regression was run on it. So this is length cubed versus weight, and then length versus cube root of weight. The data is going to come out differently, obviously, because you're rescaling one of the variables. But the residual plot, pretty much, random scatter, the things that we like to see in both of them. But you'll notice that if you cube the length, well, that scale is dramatically different. And the residuals are much bigger. Versus over here, if you cube root the weight and length stays fixed, these residuals are much smaller. So the scale of everything's going to change. Not to say one is necessarily better than the other. These R squareds are both very strong positive linear relationships. So we're fine in either parameter. If you were to take this first one, this would be predicted weight, and then we're looking at this guy here, that's A and B. So predicted weight equals 4.066 plus 0.01467774, and this is length cubed. So it's important that you call it length cubed, because that has an entirely different meaning when we make the prediction. Similarly, if I were to use the second transformation over here, this would be the cube root of weight hat equals negative 0.02204 plus 0.212. I'll get there. 4161. There we go. And that is length. Let me take that back. You guys forgive me. 0.246616. Too many 2, 4s, 1s, and 6s. I was looking at S instead of the coefficient of the x variable length there. But we finally got it together. Each of those equations would be fine to use. Scrolling down here, suppose a contestant in the fishing tournament catches a rockfish that is 36 centimeters. Use the two equations that we just found use the model from part A to make predictions of the weight. So, give the equation of least squares regression line. So we'll do it for both. We'll do it for transformation 1 and transformation 2. So weight hat equals 4.066 plus 0.01467774, 36, and that's going to get cubed. That's length cubed versus the cube root of weight hat, which is negative 0.02204 plus 0.246616, 36, not cubed. All right, we're just going to plug that one in, and then we'll transform it. So looking at the first one, just plugging in 36 cubed, we get 688.9 grams. If I just work this out, I'm going to end up with the cube root of weight hat equals 8.856. Now that's not the answer. That's the answer for the cube root prediction. So to undo this, I'm going to cube both sides and get predicted weight equals 8.856 cubed, which is 694.6. So very close, these two answers. Again, there's going to be a little bit of flexibility based on the rounding and the limitations of what we're doing, but both are equally good predictions about the weight of a 36 centimeter long rockfish, or whatever it was. Now we said each of the parameters, the equations, the alphas and the betas are different. or the A's and B's, excuse me. And then the S is different for both, S being the standard deviation of the residuals. Now, if you've transformed the Y, that's going to change the residuals, because remember that the S is in Y units. It's the vertical distance. So for transformation 1, the standard deviation of the residuals, S equals 18.841 grams, means that predictions using that model, we'll say model 1, will be off by an average of just shy of 19 grams. And then for number 2, where S equals 0.124161, we would say predictions of the cube root of fish weight using model 2 will be off by an average of about 0.12. And again, that's the cube root prediction. So you'll undo that by cubing it at the end. There's another example where we've got this relationship that takes off very rapidly there, more of a, looks like exponential relationship. The number of transistors is going to double every 18 months. So here's this new relationship. And again, would undoing the exponential y, as it would seem here, work? Would it fix what's going on? So to undo an exponential would be to take the log of y, and in this case it was natural log. But you could take common log if you wanted to try that. But here's a scatter plot of natural log, because it was exponential, and the inverse of the exponential is the log. So it's much more straightened out, which is great. That was what we were hoping for, and we're given the computer output there. Okay? So really, if it seems to be exponential in relationship, then x versus log y is a great strategy to try and fix that. That's kind of the argument here. So x versus log y if the relationship seems exponential. And it worked, so probably was an exponential relationship. So given all that, we're going to define this as natural log transistors hat equals 7.0647 plus 0.36583, and this is years since 1970. There we go. There's our equation. Using that equation, predict the number of transistors in 2020. Ooh, gotta update this example. Transistors hat equals 7.0647 plus 0.36583, and that's going to be years, which was 50 years. 2020 is 50 years since 1970, and we get 25.3562. Okay, so that's natural log transistors equals that. And hopefully you recall log base b of a equals x, b to the x equals a. That's our relationship there. Turning a log expression into an exponential expression is then going to get us log base E transistors equals that. So the transistors prediction is E to the 25.3562 power, or yikes, 1.028 times 10 to the 11th. It's a lot. So to exponentiate when you get that log equation there, which is maybe a case for the natural log, but you end up with this very large number of transistors. The residual plot is shown in part D here, and discuss what that tells you about the appropriateness of the model. It seems to be a pattern in the residual plot. So in another world, in chapter 3, it'd be kind of game over, with the residuals going from positive to negative to positive as we move left to right. But ultimately, because we're using transformed data, the residuals are small, relatively speaking, and it's such a better model when we transformed it from the original that in chapter 12 here, doing transformations, we're not going to put as much stock in the residual plots. So while a pattern exists, because ultimately the residuals are pretty small relative to the scale of what we're talking about here, and our scatter plot was so much better than the original one, we're reasonably comfortable, okay or comfortable with our predictions. And again, because the scatter plot much better from the transformed data, and resids relatively small. So don't sweat the residual plot too much of transformed data. Do the transformation. Does it look better? If yes, then go ahead and feel pretty good about making the prediction there. Here's another example. Distance from the sun in astronomical units versus period of revolution, or Earth years. Describe the relationship that exists here. Again, if you tried to fit a line, probably a pattern in the residual plot there seems to have some kind of look like that. Could be quadratic, could be cubic, could be logarithmic, who knows. But there appears to be still strong and positive, but it's a curved relationship. So remember, describe a relationship in the case of bivariate is strength, direction, and form. So strength, direction, and form. The best that we could say is curved at this point. I don't know specifically what the relationship is. And so that brings up a good point of, okay, well, if I don't know what the relationship is, because I don't know that it's logarithmic, what do I do? Well, you can see that what's been done here is the y has been logged, natural logged. And here's the relationship that we got. That doesn't seem to have worked. It didn't make it better than what I had, just logging y. So the question becomes, well, what do I do? Well, the strategy is going to be to log both, log x and log y. Because what that's going to do is, if this happens to be some sort of power relationship, squared, cubed, fourth degree, whatever it is, if you log both sides, it's going to transform it and eliminate the effect of the power. So logging both is going to be your strategy when you've got some sort of power relationship. Okay, so this is what we call a power transformation, and this is exponential. And the reason we call this one exponential is because it worked for exponential relationships, just logging y was the fix. For anything else, you're going to log both, which is called a power transformation, and hope for the best. And clearly that seems to have worked here. So anyway, this one's better, the power relationship. The Minitab output of the regression for the transform data for the power transformation is shown here, and write the equation. So natural log period hat 0.0002544 plus, let's try and squeeze it in here, 9986 log distance. Yikes. No hat, not a prediction, but still it's been logged. So natural log distance there. Fair enough? All right, let's take a look at using this model here. So natural log period hat equals 0.0002544 plus 1.49986, and let's see, we're plugging in that number of AUs, 102.15. And we work that out, we get the natural log of the period hat equals 6.939. And again, to get period hat equals e to the 6.939, because it's the natural log of the period. So to the nearest year, we'll say 1,032 years. Again, in D here we have a residual plot for the regression. In part B, do you expect your prediction to be too high or too low, or just right? Well, clearly there's a pattern in here. And when I tend to have log distance that's between, I don't know, let's say 0 and 3, I tend to have observations that fall below the line. And remember, this is the prediction line, this residual line. So in this area where the line is above the points we saw, this is the prediction. This is y hat. So the prediction is too high between here and here. Out here, where the points fall above the line, above the prediction line, this is going to be too low. The prediction is too low. And we had the natural log of distance was 6.939. Natural log distance 6.939. Too low, because it's going to fall out here. All right, so let's sum up what we have. And it may seem like a lot, but really there's two options. If there's a nonlinear relationship, you're asked to do a transformation. Really, either you're going to log one or both of the variables. Those are the strategies that we pretty much limit ourselves to. If it tends to be some sort of power relationship, then likely you're going to take the square root of both, log x and log y. And if it happens to be an exponential relationship, you'll likely just log y. So this exponential model, well, let me go back here. You can, again, you could do this, power and root options, but that would require you kind of needing to know the relationship. You would need to know that it's a square or a cube relationship. So that's what we did with the fish, but that doesn't really come up in what we do. So don't worry about those. Really, we have log y and log both. Those are really our two relationships here. To achieve linearity, when the relationship is exponential, take the log of y against x. If it's a power relationship, log y versus log x. Those are the ones that you're going to be asked to carry out. And for the most part, as you'll see on the problems you're about to try in the worksheet, the transformations have been done and you have to assess. It's going to be a rare instance where you're given the data, like I give you this, and you have to, log if this is your L1 and your L2. It's a rare instance where you have to carry out the transformation. But your idea would be try logging y, see if that works. If so, it's an exponential relationship. If not, try logging x with log y and seeing if that works. And that's what we call a power relationship. So go ahead and give transformations 1 and 2 a try, and we'll pick it up after that. Thanks.